Hi there, and welcome to my AP Physics 1 lesson on circular motion. So, there's lots of things to talk about. I think that I'm also going to talk a little bit about some rotational motion concepts just because there is some integration between the two things. I'm going to also try and keep those separate as much as I can, at least for now. So let's go ahead and get started. So let's look at this scenario where there is a ball on a string, and that ball is whipping around. So let me just go ahead and demonstrate that. So this thing is going around in this sort of way, and we are looking at this thing going counterclockwise, and this is viewed from above. So viewed from above, this thing is whipping around counterclockwise, and let's just assume that it's a fairly horizontal sort of plane that it is moving on. So let me kind of stop it right here, right about there. And so it is moving towards the left at that moment in time, and its velocity is to the left. But what about its acceleration and its force? So the acceleration and the force. So the acceleration and the force are both acting down. So there's a center-seeking force that is known as a centripetal or centripetal force. I prefer to say centripetal because it helps me spell the word better, and my English college professor said it that way. And of course, any force is equal to ma. Now what's interesting about this is that this is actually the sum of all forces. The sum of all forces are acting towards the bottom of the page in this case, because it's the only force that we are concerned about. There is that flat horizontal plane when you're looking at it from a side view, and so there's a force of gravity acting down, but let's not concern ourselves with that at this exact moment. I'll get to that in just a bit. So the force acting towards the center, the centripetal force, is acting towards the center, and we can express that. And of course, since this is the sum of all forces, the net force, then that means the acceleration must also be towards the center. And so we're going to express that as mv squared over r. Okay, the acceleration is v squared over r. So the acceleration of any circular moving object is v squared over r. That is the centripetal acceleration. Okay, so let me go ahead and address this idea of this ball on a string. And there's something important that I'd like to address, is that if the string were to break, or were to let go of the string, what would happen to the ball? At this moment in time, the ball would move towards the left. Of course, I have my whole dotted line moving with it, but you get the idea that the whole ball would move to the left and would move along this linear path off to the left, on and on and on. And it would not veer off in any sort of way. A lot of people have the confusion that the ball would have this sort of outward curving path, and it would not. That is not what would happen. So why do people have that confusion? I think a lot of people tend to think that there's an outward acting force, and basically there's not. There kind of is, but there's kind of not. And so let me get into that a little bit. So let me start with this ball on a string. So I just kind of taped a string to a bouncy ball. Sure, it's not a tennis ball. You have to excuse me on that. And what I'm going to do is I'm going to treat this in a linear sort of motion and give you an example. So what happens in a linear sort of perspective if I were to move my hand in this direction and accelerate my hand? I'm going to try and demonstrate this slowly. So when I accelerate my hand into this direction, okay? So when I accelerate my hand into that direction, the motion of the ball does not translate in that direction immediately, does it? It has inertia. And so when I do that, it lags behind. And then by the time it gets a chance to actually move, the force acting on the ball is not in that direction. It's up and at an angle like this, okay? So by the time that there's any additional tension in the string, you've got, we can break it down into forces. There's a little bit of force this way and a lot of force that way. So as the tension increases, what's going to happen? It will translate to the left, but it will also lift up, because as the tension increases, right? And so I have an elastic band, so you can imagine the force of tension increasing. So as that happens, the force of tension in the up direction also increases. and it's going to lift up a bit. And because it has inertia, it lags behind. And the faster I accelerate my hand, the more it's going to lift up, and it will have a limit of going totally horizontal. It'll never go totally horizontal, but if I were to accelerate my hand faster and faster and faster, it'll go closer and closer to the horizontal. So imagine that I had the ability, and I don't, but imagine I had the ability to just run that way super fast and always constantly accelerate. It would be lifting up and up and up and up and eventually get close to horizontal, and as I continue to accelerate, it would have that sort of motion. And so if we translate to a circular moving body, I'm going to move my head out of the way. There we go. That is why this ball lifts up. I'm going to use some air quotes there. So what's happening here? Well, let's go this way. That way I'm a little bit better in frame. And so what's happening is the slower I move, the slower the ball's moving, the lower the acceleration there is towards the center of the circle, which means that it's not going to lift up as much, for the same reason that if I accelerate my hand at a slower rate, it's not going to lift up as much. So, so if I go really fast, there's going to be a limit to where it could go close to horizontal, but not quite. And what's happening here is as the ball is coming towards you, right, that's its direction of velocity, I pull this way. And then by the time I pull this way, it's now changed its motion. Now it's going this way, and I pull towards the center. It's going this way, and I pull towards the center, and so on. And so as I always keep pulling towards the center, then it will, the ball has momentum, right? It has momentum in any particular direction along the tangent. Okay, that is the name of this direction. So the name of this direction is the tangent. It's a linear velocity, or otherwise known as a tangential velocity. And it will always have momentum in that direction. It lags behind because of its inertia, and so that's why it lifts up. And so the problem here is that it appears as if there's some sort of outward acting force, even though there's not. So when you're thinking, or when you're looking at this, you might be thinking that when I pull it in this direction, if you were just kind of like watching me as I go by with pulling this thing, you might think that there was some sort of force acting in the opposite direction, causing this thing to hold back or lift up or something like that, but there's obviously not. And so in the same way, when people look at circular moving objects, they might think that there's some sort of force pulling the ball outwards, but there's obviously not. If we let go of it, it would come straight to you. There would be no curving motion. The other issue too is that if you were in a car and you are a litter bug and you throw some sort of like, a bit of litter outside of the car window, what's happening here is the car is moving, if I can draw it really quickly, the car is moving along a tangential path, right? So it's moving in that sort of direction. I'm just going to really extend this out. So that is its velocity off in that direction. And of course there is an acceleration that is acting towards the center of the circle, so that is the direction of its acceleration. Right? Here's its acceleration, and here is its velocity. And so if you were to toss something outside of the window, let's say you don't really give it very much velocity in any particular direction, it just has velocity just like the car does. So you kind of like, fling it out the window because you're a litter bug, don't do that. What would that piece of litter do? Is it would move directly along this path while the car, let me even switch colors, the car would continue to move in a curved path because of the friction between the tires and the road. And so in your perspective, it looks like the litter is moving away from you. But in fact, it's going straight and it is moving away from you, but it makes it look like that the litter is the thing that is curving. I don't think that our brains are designed to be in a rotating or circular moving reference frame. So when you are inside of a circular moving reference frame, things can be a little bit wonky, and we'll get into that in a little bit. So let's continue to look at this car in the road situation. If I can back up and get rid of some of my marks. So as we said, we have the car's velocity moving in this direction, so that is its velocity. And then towards the center we have, of course, our acceleration acting towards the center of the circle. Okay, so here's our acceleration towards the center of the circle, which is, of course, v squared over r, and we can express that as, as our force as well. That's the direction of the force, which is m v squared over r, as we said. So this is just an equation that expresses that it is a centripetal force, that it is a force that is causing something to move towards the center of the circle. But what is the nature of that force? This is what you must think. What is the nature and the origin of that force? So what is causing this car to move around the corner? And you should recognize that the force acting on it is the force of friction. It's the friction between the tires and the road. And assuming that the road is a flat level surface, then you should recognize that this force is also the force of friction. They are one and the same. And what is our equation for the force of friction? It is, of course, mu s times the normal force. Remember that it is, in fact, static friction because it is a different point of contact between the wheel and road with each moment in time, so there's no sliding that's occurring, and it is static friction. And since it's a flat level road, then of course, right, so side view between the wheel and the road, you have the force of gravity, mg, acting down, and you have the normal force acting up. And so this is really mg in this case. If it's not a flat level road, of course, you'd have to consider that and figure out what the normal force is, and we'd have some other issues, and then you'd have a banked turn problem in that case. But let's keep this fairly simple at the moment. So let me go ahead and do a substitution of mg in this case, because as long as it's flat level road, I can do that. And so what's nice about this is if you take a look, then m cancels out. So it doesn't really matter, at least theoretically, whether this is a small little sports car or a giant truck. In either case, the factors that determine how fast the velocity, right, how fast the car can go around the turn, is really just a function of the coefficient and the radius of the turn. And of course, you know, the fact that we're here on Earth. So given that the coefficient of friction is the same, so it's the same type of rubber on all the different tires, assuming that we're all on Earth, then all vehicles should be able to go around a certain radius, right? Here's our radius of the turn. And yeah, so all vehicles should be able to go around at the same speed. Pretty interesting stuff, right? Okay, so let's kind of move on from there. Oh, I'm back. So let's look at simulated gravity. So in this scenario, let's pretend that this is like sort of a giant Ferris wheel kind of a thing, but it's out in space, so there's no gravity. So what's going to happen is we can simulate gravity, and it's done very well in a few different movies. 2001: A Space Odyssey is sort of that classic, famous movie that was the first one to ever do it in a very good way. And so here's how it works. So you have this giant rotating sort of cylinder platform kind of a thing, and in fact, maybe if I can draw it in perspective, so that way you can kind of have an idea. So let me just kind of redraw this structure. So I'm going to kind of make it a three-dimensional sort of thing. So just imagine that it's a cylinder, okay, and you've got this person over here, and then you can also have another person over here, and so you're looking up, and the next guy is up ahead of you. But the way I have it drawn is you basically have it subdivided into all these rooms. So this person is in their own room, this person is in their own room, and it's just a giant cylinder with some pretty wide diameter. And so this thing rotates, okay, this thing rotates in this direction, and this person is moving in this direction along their velocity, but because as they move that way, the floor of this cylinder is in the way, it pushes them towards the center, and it creates a simulated gravity. So let's look at what's really happening here in a fine-tuned sort of way. So what's happening here is this guy's holding a ball, and he drops the ball, literally, not figuratively. And so what's happening when he drops the ball? So this man, the room, everything, the whole thing, let's say, is rotating in this direction. So at this moment in time, he has a velocity, okay? He has a velocity that is in this direction. And so does the ball. And so when he releases the ball, he lets go of the ball at this moment in time, the ball is going to follow this straight line path, and it's going to wind up here. The man, however, has a force, and it's actually a normal force from the bottom of the room. He has a force acting up towards the center of this circle, right? So it's a force acting towards the center of the circle, and it's constantly changing in that it's changing its direction, but it's always towards the center of the circle. So when it's over here, it's still towards the center of the circle. And so it's changing his path. He is accelerating towards the center of the circle. He's not getting closer to the center of the circle, but he's always accelerating into that direction. He's not changing his speed, he's changing his direction. He is accelerating. And so by the time he gets to here, the ball is here. And in his perspective, if he did not know that he was in a rotating reference frame, imagine that we have a physics party, and I have this example every year, that we decide to have a physics party. We come into my classroom and we just do lots of demonstrations, drink lots of soda, and have our physics high. We all fall asleep on tables, and then because I have $1 billion, I have the entire classroom removed as you guys are asleep, removed from the building, sent up into space, put into this giant rotating platform, and the next morning you guys wake up. Of course I have the shutters closed and you can't see outside. We wake up in space, we are in a rotating platform, but you don't know it. You have no idea that you are in space. You would have no indication that you were in space whatsoever, because it would still seem like gravity. And I tell you, you're in space right now. I just put you into space. You would say, no, I'm not. Look, watch. A ball just fell to the floor. And that's my proof. And I would say, no, this is what's happening. You, in fact, are actually moving along a tangential path. The ball continues to move along that tangential path while you move in a circular path. The ball moves along a linear path and you move along the constant changing tangent, but you know what I mean. And so you would say, well, maybe there's another way that I could prove it. And there is, actually. What could you do to prove that you're moving in this rotating reference frame? You can run. What if you were to change your velocity? Just by sheer standing here, you're inherently moving in this direction at some given velocity, the same tangential velocity of the platform. But what if while standing on this platform, the outside part of the cylinder, you decide to start running in this direction? So you've increased this velocity. Now, you've increased your velocity. The radius is the same. You've increased your velocity. Your acceleration is going to increase. You would feel heavier. Keep in mind that it is the normal force acting up on you that you feel that's going to give you that perception of gravity. In turn, the floor feels a reactionary force acting down. Okay, we would call that, and there's a name for it, and I hate this, but it's known as the centrifugal force. It is an outward acting reaction force, and it is only in existence as a reaction force. There is nothing actually pulling outwards, just like I had expressed with the string that the ball fell on the floor. But there's no force acting outwards. There's no force acting outwards. There is a force that is reacting outward. So keep that in mind, and so we've got this method where you can increase your velocity in this direction. It would increase your perceived acceleration, not perceived, your actual acceleration. You could run in the other direction. In fact, how about if I leave you on this idea? What if we start running in the opposite direction? So let's move it to this point here. So you're just by standing there, you're moving in this direction at a velocity of v. And then you decide to run in that direction at a velocity of v. You're floating. You would actually start to float because you're not actually moving. The whole habitat is rotating while you're just staying in the same spot in space. And you would just float there. So you would no longer have any simulated gravity anymore. So there's a couple of very neat examples. All right, so let's see if we can move on a little bit. Tell you what, let's just kind of end on this whole idea. So we have a force of gravity acting, what seems to be like a force of gravity acting down. That's the centrifugal force. and so the normal force is acting up on you, and you act onto the platform. And so keep in mind that these forces are just an action-reaction pair. And so this is sort of like my zoomed in little thing on this guy. He's moving to the right, the ball's moving to the right, and so the normal force is what's acting on you towards the center. For the ball, it was the force of tension, but it is effectively kind of the same idea. We could also look at one last thing. If I have a ball on a string and that ball's not totally horizontal, and so I'm going to give a ghost image of the ball on the other side when it whips around, so I'm moving that string around, then I would say that I can break these forces down into their x and y components. So let me just look at one side of it. So if this represents the forces, so this is the force of tension in the string, this is the force of tension in the x direction, and this is the force of tension in the y direction. So there's a force of, let me see if I can move this stuff down for a moment. That'll work. And so if I have a force of gravity, mg, acting down, in the sum of all forces in the y direction must be 0, because it's not accelerating up or down, it's only accelerating left and right. Then I can say that negative mg is equal to the force of tension in the y direction, right? And so that allows you to figure out what this y component of the force is, which then allows you to kind of look at this component of force. You can now translate that using a little bit of trig. You can kind of figure out what this force is, and then you can actually look to see what the acceleration is. So I just want to get your mind kind of moving in that sort of direction, and I think we will explore those things a little bit more moving forward. So I think I'll leave it at that for now, and I will see you guys next time.